My name is Pagano. I'm a new student here in the PhD program at MEN, working under Dr. Leslie Leverson. I'd like to just walk you through today a quick problem using a beam and trying to find the reaction forces in the basic beam statics problem. So the first thing we're going to do is model our problem as being our basic beam. Of course, the beam is going to be resting on two different points, which are known as our reaction forces. If we had these just set up as pin connections, what we wind up having is something called an indeterminate beam that we're unable to solve using basic static principles. We have to go into mechanical materials or deformable bodies or something like that to really analyze what's happening. What we can do, however, is turn one of these pin connections into a roller connection. So, who here can tell me the difference between a roller connection and a pin connection?
Roller connection only has sorts of reaction forces in Y.
And why might that be interesting to us then if we're looking at a beam problem? If we're thinking about some of the forces. What's that? We'll learn that here. Okay, so you're right. The reaction force that has the rollers is only going to have a reaction in the Y direction, whereas if we have a pin connection, we're going to have a reaction in both the X and Y direction. Let's expand upon this a little further, then we'll actually put some loads in here, and say that we have something right here called load P. And we're also going to have a distributed load on this half of the beam, which we're going to call omega. And I'm going to go ahead and give you guys some information about this. We'll say given that P is equal to 100 pounds, it's a 100-pound force pushing down on the beam. The distributed load omega we're going to have as 25 pounds per foot. Meaning for every foot that this is distributed, it's going to be distributed down 25 pounds. We'll throw some dimensions in here too. So we'll call this 2 feet from the reaction to load P. We'll call it 2 feet from load P to the start of the distributed reaction. And we'll call the entire distributed load a 4-foot long load. So as we know, if we have two reactions, we'll call these guys our reaction A and our reaction B. RA and RB. And you had already explained that one of these reactions is only going to be in the Y direction, the other one's going to be the X and Y direction. So our pin connection will wind up having these two forces here, whereas our roller connection is only going to have the single force pointing up. Our RA is only going to have the one value. What's nice about this, though, is that we have a beam problem where all of our loads are going in the vertical direction, the Y direction, which means right off the bat, this load that's showing on our beam in the X direction, we know is equal to 0 from basic statics. There's no other loads in here, so the sum of the forces in the X direction are going to be equal to 0. However, we can't just look at that and say, all right, what's the sum of the forces in the Y direction? Because we have two unknowns, and we're not going to be able to solve that problem. What we can do, however, is try to take a moment from one of these ends. So, which end would we want to take a moment from that would make this easiest? Anybody have any ideas?
The one without the roller.
The one without the roller, so you want to start the pin connection?
Yeah.
Okay, let's start the pin connection then. So we're going to take a similar moment about point B. And since we're working with statics, we're going to say this is equal to 0. So let's work our way across this. What's our first reaction going to wind up being? Well, if we're looking at this distributed load, we know this distributed load is 25 pounds per foot, and we have 4 feet. We can treat this entire distributed load as a single concentrated load located midway in the distributed load. So if we were to do that, this load of 25 pounds per foot becomes a 100-pound load that's distributed 2 feet out from reaction B. So for our moment, we're going to have this, and we're going to use our right-hand rule with positive coming out from the board. We'll call this reaction being our omega is 25 pounds per foot, times the distance of 4 feet, times the reaction distance of 2 feet, gives us our first piece of what's pushing this down. As we keep working our way across the beam, we're going to get to our load P, which we were given and told that it's 100 pounds. So as we get to point P, we know that we're 4 feet out, 2 feet out, gives us 6 feet out, which means our next reaction is going to be also an addition, using our right-hand rule going this way, and we're going to have a load of 600 foot-pounds, just by doing the 100 and the 2, and 100 and the 6 rather. Finally, we get to the other end of the beam where we have our unknown reaction. This is what we were looking to solve. So now we can say, using again the right hand, the right hand rule going into the board is going to wind up being negative for us. We'll have a negative RA times a quantity of 8 feet. So from this, we can tell me what the value of RA is going to be. Anyone? RA is going to be equal to 100. So come up here and say what we're looking for. Our RA, we know, is equal to 100. This is kind of convenient. We know that our reaction P is 100 feet. We know our distributed load of 25 per foot is 4 feet long is 100 feet, which means we have 200 going in the y direction. We can easily look at this and write it out and say, yeah, the sum of the forces in the y direction equal to 0 is going to be equal to our load P, which is our negative 100, our distributed load being another negative 100, our reaction load A that we just picked up, which is a positive 100, and finally our reaction B, which is going to be 100. So now we found our reaction B is equal to 100. Let's pretend that.
You're almost done. You're done.
I'm almost done.
Yep. So you had to engage in it.